The purpose of this next example is to illustrate that in a differential equation, the independent variable doesn't have to represent time. So in this case, the independent variable will be a spatial variable. Let's suppose we have this system of coordinates, x and y. X is going to be a horizontal displacement and y a vertical displacement. And in fact, x is going to be the independent variable in our differential equation in this case. What is our differential equation going to do for us? It's going to let us find the shape of a hanging cable. So suppose that this blue line represents a hanging cable. H represents the tension on the cable at this point where x equals 0. Let's just write that. And we're going to assume that the cable is level at that point where x equals 0. Here where x equals x, if you like, the tension is T of x. The tension is going to vary along the cable, so the tension T will be a function of x. And let's suppose that at this point x, the slope of the cable is given by this angle theta here. Let's say that the weight of the length of cable between 0 and x is given by W of x. Now we'll be able to get a differential equation describing the shape of this cable just by considering Newton's law. This is a problem in statics. We assume that the cable is still, so the horizontal and vertical forces on the two ends of the cable will have to balance out. So by Newton's law, we will first have that the horizontal force on the right-hand end of this section of cable between 0 and x is T of x times the sine of the angle theta. Sorry, that's the vertical force. T of x times the sine of the angle theta. That has to balance the weight of the length of the cable between 0 and x, because we're going to assume that the slope at the point x equals 0 here is 0. So this has to equal W of x. Now if we consider the horizontal forces, on the right hand side we have a force of T of x cos theta pulling to the right. That has to balance the tension H at the other end of the section of cable. So that's what Newton's law gives us, and we'll see that this leads to a differential equation. In particular, we can divide, and then we get, then T of x disappears. We get the tangent of theta is W of x over H. What's the tangent of theta? That's the sine of this angle divided by the cosine of this angle. Well, that should just be the slope of the cable at this point x. So in other words, tan of theta should just be dy by dx. So that gives us a differential equation right there, except that the form of this function W of x has yet to be determined. We've just left that as a function. The weight of the length of cable between 0 and x is W of x. And in fact, there are different possibilities you might like to consider. Let's suppose that we're doing some civil engineering and we're building a suspension bridge. In that case, the weight of the cable itself is not all that important. It's more the weight that the cable is supporting. So if, for instance, we have a roadway going along the x-axis here, then it's going to be the weight of that length of roadway that is W of x. That's going to dominate the weight of the cable itself. So in that case, you would think that W of x, the weight of this length of cable, or the weight supported by that length of cable, should be directly proportional to x itself. So let's consider that case first of all. So if the cable supports, say, a suspension bridge, then W of x will be proportional to x itself. So let's say W of x is equal to little w times x. So let's substitute that into our equation. Then we have dy by dx equals little w over h times little x. And once again, this is in a form that we can easily solve. So what do we get? Again, we arrange to separate the variables. So we get dy equals x dx. And it's a simple matter to integrate both sides of the equation. So we get y equals w over 2h times x squared plus a constant. So here I've combined the two constants of integration into a single constant c. So this tells us that in this case, in the case of a suspension bridge, the shape of the cable should be that of a parabola. So in this case, where the independent variable is the spatial variable x, we have used a differential equation. We've solved a differential equation in order to solve a geometric problem, namely, what is the shape of a cable in a suspension bridge. We get another result if the cable is just supporting its own weight. So suppose, then we have to find the arc length, essentially, from 0 to x. It's proportional to the length of the cable itself. This isn't quite as simple. So what we're going to have to do is look, say, at a typical infinitesimal piece of that cable. So suppose this is the point x. Let's consider an infinitesimal horizontal displacement dx and an infinitesimal vertical displacement dy, and we'll call this distance here dl. Then, thinking of this just as a triangle, because these are infinitesimals, dl must be, by Pythagoras, square root of dx squared plus dy squared. So in terms of our independent variable x, we must have dy by dx equals the square root of 1 plus, dl by dx equals the square root of 1 plus dy by dx squared. Now, okay, so what can we do now? Our differential equation tells us that dy by dx equals the weight of the length of cable from 0 to x divided by capital H. Now we're going to call the arc length, the length of that piece of cable, L. So let's say that little w is the weight per unit length of the cable, then w of x will be w times L, where L is the arc length from 0 to x, and we'll divide that by h. Now, we have an expression up above for dl by dx. So what we could do in order to work that into this expression is to differentiate both sides of this equation by x. So then we get that d2y by dx squared equals w over capital H times dy by dx. But we have an expression, sorry, dl by dx, that should be. But we have an expression for dl by dx. It's the square root of 1 plus dy by dx squared. So here we have a differential equation. If you ignore the middle part, we've got d2y by dx squared equals the w over h times the square root of 1 plus dy by dx squared. Here again we have a nonlinear differential equation because of these nonlinear terms here. And in fact we call this a second order equation because we don't just have first derivatives, in this case we have a second derivative. So this is a nonlinear equation, like examples we've seen before, but it's also a second order differential equation. It's a relatively simple second order equation because it really only involves the second derivative and the first derivative. So what we're going to do is treat it first of all as a first order differential equation in the first derivative. So we'll say, let S, say, for slope be dy by dx. Then we can rewrite that previous equation as ds by dx equals little w over h times the square root of 1 plus s squared. So that's converted it into a first order equation in S. So that's a trick that works for this example. In general, it's not that easy to solve second order equations. You can't just reduce them to first order equations as we have here. But in this case, what we're going to do is go ahead and solve this first order equation, and then we'll know what dy by dx is. And then it should be a simple matter to find y in terms of x. Okay. So, once again, yet again, we can separate variables here. So we'll get ds over the square root of 1 plus s squared equals little w over h times dx. Once again, we just have to integrate both sides of the equation. And if we do that in this case, we get the ln of s plus the square root of 1 plus s squared equals wx over h plus a constant of integration. And as before here, I've lumped two constants of integration together into one. Now we can again use exponentiation. So we get that s plus the square root of 1 plus s squared equals some other constant. Let's say this is c1, then another constant c2 times e to the wx over h, where this c2 is just e to the power c1. Now we can solve for s. That just involves some algebra. We get s equals e to the power little w over h times x minus e to the power minus little w over h times x divided by 2. That solves our first order equation and gives us an expression for s in terms of x. But again, s was simply defined to be the slope of our cable. In other words, it's dy by dx. So now we have another differential equation in y and x, and we can solve it finally to get an expression for y and thereby find the solution to our original second order differential equation. So it's pretty straightforward to solve that differential equation, and that gives us y equals capital H over W times e to the power W over hx plus e to the power minus W over h times x divided by 2 plus a constant that we can call, say, C3. But this expression, this fraction, is just a hyperbolic cosine. So this is cosh wx over h. Now, we can simplify this expression a bit if we like. We can just choose our coordinate system so that the height of the cable at x equals 0 is h over w. Then that means that C3 will be 0 because this cosh works out to be 1, as you can see from the expression in terms of exponentials. Both of these exponentials will turn out to be 1, so this whole thing will work out to be 1. And then we will get h over w from this term, so C3 will just be 0. So then we get y equals h over w times the cosine of wx over h. And this curve, this hyperbolic cosh, is often called a catenary. And catenary is just Latin for chain. And that's just because, of course, it's the solution to this differential equation that we've just solved. What's the difference between a parabola, which we got in the first case, and a catenary? Well, if a parabola looks like this, a catenary is a bit sort of squarer. The sides comes down more steeply, but then has a sort of a squat bottom. Now, we applied a couple of initial conditions. We applied 2 initial conditions, which is normal when you have a second order equation. One was that the slope was 0 at x equals 0, and the other was that the height at x equals 0 was chosen to make that constant c3 vanish. Without those initial conditions, we would get a general expression for all of the possible solutions. So we would have had y equals h over w times the hyperbolic cosine of w over h times x plus one constant, say c4, plus finally another constant added to the whole thing, which was our c3. And the c4 would be the natural log of what we called c2. Now, you don't have to use initial conditions. In general, the values of the constants, namely c3 and c4, might be determined by boundary conditions. Essentially, if you apply conditions for two different values of x, you usually call them boundary conditions rather than initial conditions. So for example, we might specify that y of 0 is h over w, as we had before. And then we might say that the value of dy by dx at, say, the point x equals 10, h over w equals the hyperbolic sine of 9. And then that would let you work out the values of c4 and c3 and get the particular solution that corresponds to these boundary conditions. And we just use the term boundary conditions here because, again, this condition applies at x equals 0, but this condition applies at x equals 10 times h over w, so at another point for another value of h. So boundary conditions is just a more general term, really, than initial conditions. If we only apply boundary conditions when the independent variable is equal to 0, then they'll almost invariably be called initial conditions. But this is all really just a matter of terminology. The details of the expression that you get with these boundary conditions are worked out in the notes, but that doesn't really matter. Those details don't really matter. So if boundary conditions are given instead of initial conditions, then we say that the problem is a boundary value problem. So the problem of solving the differential equation subject to those boundary conditions is called a boundary value problem. But as we've already said, if initial conditions are specified, then it's called an initial value problem. And this course is almost exclusively concerned with initial value problems. So we might mention that so far the examples that we've seen have allowed us to find solutions relatively easily. In fact, we've always found those solutions by the so-called method of separation of variables, putting different variables on different sides of the equation and then integrating. The examples we've seen are cases of exact differential equations. And those are just differential equations that can be solved by integration. Not all differential equations are of this sort. And in general, you just have to be clever in order to solve differential equations. The only class of differential equations for which there are standard uniform methods of solution are the linear differential equations with constant coefficients that we'll be focusing on. And our first example involving exponential growth was an example of that sort. As I said, this last example that we saw was an example of a second-order differential equation because it contained a second derivative. The other examples were first-order differential equations. We'll end this lecture here, and then we'll take a brief look at one further example. It's an example of a partial differential equation, so called because it contains partial derivatives. Why does it contain partial derivatives? Because it's an example where there is more than one independent variable. In fact, there's going to be a spatial variable and a time variable. We've just seen an example where the independent variable, the one independent variable is a spatial variable. We could have both time and a spatial variable. So we'll take a quick look at an example of that sort in the next lecture. See you then.